in 2 weeks' time, we have covered everything you need to know for that last C++ assignment. It's about templates, but you will have to combine templates with dynamic memory allocation, write copy constructor and move constructor, copy assignment, move assignment for these templates. We talked about those, but for different types, classes, simple classes. You have to now extrapolate and use them for templates. It's not a big deal, but it will be interesting. So, we are looking at looking at iterators yet. We have to finalize containers. We have started talking about that. We talked last time about sequential containers. We haven't touched associative containers and neither container adapters. Associative containers are those for sequential containers first. Vectors, list double-ended queues. Associative containers, set, multi-set, map, multi-map. This is the set of containers we are touching. And you will see that container adapters use, for example, a vector as a base and construct a stack. For people who did the data structure, stack is a data type where you work with elements at the top, like a stack in a cafeteria. When you add an element, you add it at the top. When you take an element, you have to take it from the top. And then there are queues, first in, last out, and things like this. First in, first out. This is a queue. So container adapters are based on either vector or double-ended queue, but come with some operators. And we looked at vector, and we have seen that the sequence containers come with a set of common method. Push back, pop back, good for all containers. Vector is very efficient with working at the back. List is efficient to work with every node. Double-ended queue work with front and back. And here I said we have a presentation done by Straustrup, the essence of C++. It was at Edinburgh University, and he talked about various versions, but if we go to 56, okay, come on, to move it.
It's the volume.
It's stopped here. Oh, it's the volume, sorry. So stop. 450. I said 50. It was 54. It's when he starts talking about templates. 54. Okay. And then we put the volume here and we start.
So, that said, I'll go on to the next thing, which is generic programming, which has been widely popular and successful in the last 10-15 years. So let's look at that. I'd like to point out that the first paper I ever wrote on C with classes, C++'s predecessor, included generic programming. And I explained why I really wanted a vector of t where t was a parameter, and I really wanted operations of vector of t's that had t as a parameter. I mean, if I have a vector of t's, I want to sort a vector of t's. I don't want to fix t arbitrarily for operations. So I wanted that, and I wrote widely that you could do that with macros. That did not scale. It's a lousy solution. In '87 or so, I decided that we needed something better. We needed something extremely general and flexible. I never trusted the science that could only do what I imagined. And I wanted zero overhead because I wanted to put C arrays out of business if I could.
C array out of business
is my least favorite data structure. It is the ideal structure for accessing memory directly. But most of the time, that's not what we want. C arrays has a tendency of losing their size. I mean, with the slightest excuse, an array turns into a pointer to one or more elements. Actually, it turns into a pointer. Yes, that's what it does, one or more elements. Except that other pointers can refer to 0 or more elements. This is the source of a lot of problems. So basically, I wanted to compete with that because I wanted data structures that, for starters, did not convert to pointers and remembered their size. And then I wanted well-specified interfaces. I pointed out one of the very first things I did with C++, with C when I built C++, was to provide better type checking. So obviously I wanted interface checking for this. And I looked at it, and at the time, nobody knew how to do those three. And I couldn't figure out how to do it. Given the constraints of my overall problem, I had to pick the two first. And you know, 2 out of 3 ain't bad, but it doesn't feel good. It doesn't feel right. And so I've been trying to solve that ever since. And I actually do have a solution, which I'm going to show you in not too great detail. But let's first see how templates have worked up till now. You can write yourself, you can parameterize a type, then you can parameterize an algorithm with a type, and most of the time you have to be explicit about the type of a type, sorry, the parameter to a type. You don't have to be it for a use of that type. You simply deduce what t is. If that v happens to be a vector of integers, obviously the t that parameterized sort can be implicit, and it'll be a sort of integers. If it's a vector of strings, it will be a vector, you'll sort strings. Fine. What you can do here is anything that you can call it compile time duck typing. Duck typing is a general principle that if it walks like a duck and it quacks, it's a duck. In other words, you just use the argument type, and if it worked, it worked. And if it didn't work, you get an error message. The only good thing about the error messages you get is you get it at compile or link time before the program gets shipped to a customer. The bad news is that these error messages can be spectacularly bad. My best example recently was I had a 7-line program that used one little parameterized class, and I was using Sigwin on a Windows machine, and I never figured out what the first few pages of the error messages was because it blew my Windows buffer, Sigwin window buffer. Then I tried another compiler, and I got the same result, except that the error messages were totally different, and it had nothing to do with the code I wrote that was in any way obvious. So we really should deal with this. So I'm trying. First of all, let's see, what we have found is that people write compile time programs, and they have really good reasons for it. Mostly performance, but also to express things as directly as possible. Why delay to runtime what you can do at at compile time so you get your errors and things like that. So people have been doing this. And so, like any new feature that's sort of cool, powerful, expressive, efficient, it gets overused. There's been serious overuse. In particular, people write template metaprogramming to compute values. C++11 provides you the ability to write functions that's executed at compile time, which take care of some of the worst abuses of templates. I'll get to other ways of improving that in a second. But first I'll show those of you who haven't seen all that much C++ what the code looks like. We can parameterize data types with integers, and we can parameterize algorithms with that. So I can sort the vector of integers here, and I can find my hometown in a list of strings, and the usual way to deal with returning a failure is to return the end. I'm looking for a list for something, and I found the end instead of
find returns.
That's the way it is. So we can write code like this. We parameterize element type and container type.
We don't have to know.
I can also do the find in the vector of integers, so it's generic code. That's part of the appeal of this. We can also parameterize on criteria, actions, algorithms. So here I want to have find something that not really is equal to something, but has a property. Here we write a predicate. Is it less than Griffin?
Now, this is something which was introduced in C11. Find if is an algorithm, it's a function. Takes another function as argument. This is something considered higher order function. It was introduced for the first time by functional programming, and now other programming languages like C++, Java, they are introducing them as well. So a function to takes some arguments, one of the arguments is another function. We will briefly talk, but we won't go here. These are quite advanced things. Notice you should recognize this notation. The argument is a reference to a vector, right? A vector of strings, which tries to do some searching and uses an algorithm. We will talk about an algorithm next week. So we will stop here and we will continue. As you have probably noticed, he introduced the notion of templates in the language. Standard template library was introduced by another team, and with C++ 98, I think they went and made STL the library of the language. Before we go, I want to show I recovered from my computer some library files, and I copied them here just to have a look to see what does it mean namespace standard, how library files are put into the system. This is I/O manipulation, manip file. Okay, so this is part of new ISO C++ library. It has some things there. If not defined, some name. Notice underscore blah blah blah, underscore blah blah blah. It's part of the system. If these are not defined because it doesn't want to get this file processed several times. And now namespace std. This is how a file is part of the standard template library. This is keyword is put there, the name std, and then the code is included, open curly bracket, like for a class, and then some things are included there. And when this is a type of commenting, Dixogen type of commenting for various functions or things. Again, notice that part of the library file, we have names which start with underscore. And this is why I prefer you not to use underscore as a first character, because sometimes they are part of, can be, this is at the file level, so it's not a local item. And then when the code for this is finished, you see the curly bracket ends the thing. It's like a class, but it's preceded by namespace std. So this is the end of the namespace. And then we have end if. And this iomanip.h is all it's made available in the computer system. These are with h suffix, iStream, h, iomanipulated, the header file. Normally, they are not including any code, the header file, normally. Let's continue from the current slide, or not from the current slide. What is? So, oops. Let's have a look at associative containers. They are used for searching, finding elements, or sorting elements. For sorting, we have to compare elements, and there is a default operator which is assumed to be available for elements to be sorted. So if we want to use a sort algorithm with the student class you design, you have to provide this operator. So you have to overload the comparison operator in order for the sort algorithm to work, because it relies on the existence of a comparison operator. Right. For native types, integer, float, and stuff like that, sorting is done on the less operator. And there is a possibility to do sorting in descending order, to change the operator from less to greater. Anyway, these associative containers are implemented as binary trees. Set is a collection of elements which are arranged in binary trees to allow for fast searching. You can barely notice that for this element, the one at the right is smaller, the one after it is larger. And for this element, this is smaller, this is larger. So with this arrangement, things can allow for very fast searching. For map and multi-map, we have elements made of two values, key value and associated value. So for map and multi-map, we have a pair of elements in each node. And the sorting is done on the key value. So we do searching for the key value. Right. This set allows for unique elements. In a set, you can't have a repeated element. So a set is made of 5, 9, 10, 11. If you want, you are not allowed to have 5, 9, 9, 10, 11. Multi-set allows for 5, 9, 9, 10, 11. That is multi-set, you can have repeated. But for sets, you are not allowed. And notice that some of the methods are like for vector and sequential container. Insert what to insert element, and in set this is inserted in increasing order. You will see removing all elements, erase a single element, check whether you have elements in the set, and look whether a given element is in your set. These are the common methods used for set. The set doesn't have index operator, be aware. How to declare a set? You have to include the file using namespace, and then, like for vectors, but instead of vector, you would set the type of elements in your set and choose a name. And then you can do putting elements in your set. And you will see that when you print your set, they come like this. Not in the order you have put them. 5, 1, 2, 4. No. When you insert 5, 5 is the first element. Then when you insert 1, 1 is inserted in front of 5. So you have the order 1, 5. When you insert 2, 2 is inserted not after 5. It compares with 1 is greater. It's 2 is smaller than 5, yes. So 1, 2, 5. This is how insertion is done, and this happens very quick because of the binary tree. So if you print it, we will see how to print with iterators. You go through each element, you get them in sorted order. But we will talk about this after we talk about iterators. Map, I said, contains pairs, key value pair. And the sorting is done on the key. Be aware, key can be any type for which sorting makes sense, a string included. You can have a key as a string because you can compare strings. Maps, like sets, allow for unique keys. Multi-maps allow for repeated keys. Now, how to work with maps? We have the same methods, but a little bit different type of arguments, because when we insert in a map, we need to call this function, which creates a pair from these two values. How to erase? You erase the element by erasing the key. As soon as you erase a key, the element, the pair disappears from the map. To find an element, you have to specify the key or the pair. Notice that the map comes with an overloading for the index operator, but be aware, this M key sets the element identified by key. So if I say M key equals M3 equals here, what I do, I create the pair 3 and here and put it into the map. And this works in both ways. I set the element, or I just display cout M of 3, and then we get the value associated to key. This doesn't do any checking for the existence of the key. This does checking at. So like for strings or array, this is a difference of index and at method. And here we have an example of how to use a map. Include the proper file, and then declare your object. In our case, we want the key to be of string type and the value associated to be an int. We can think of situations where you might want this. Name and ages. So this is how we create elements and add them to our map. The first pair, string, is a key and 1 is the second component of the pair. Then test and 5, wrong place. And they are put in increasing order, lexicographical order in the map. But we can get handle to 1 just with this cout, the value associated to string in map. So this will display 1, 5, and 0. But be aware this index notation works a little bit different than compared to index in an array. We don't have a sequential array here. We have a binary tree, a map. Anyway, for the moment we won't use a lot these associative containers, but you have to know what are the main differences. Multi-sets and multi-map allow for repeated values in a set and in a map. A multi-set contains a value multiple times, and a multi-map has multiple elements with the same key, which is an interesting thing. Container adapters, stack queue priority queues, last in, first out operation. For such abstract data type, what you have is push and pop, 2 operations in general, push element and pop element. And this goes to the top of the stack. And then you can check whether your stack is empty or not. You can clear the stack if you want. For queue, we have the model, a real queue for your staying in queue in a line at a bank. First in, first out. The first customer in is the one who is served. And for a queue, we have different operations. On queue, which means add to the queue. DQ, take out of the queue, 2 operations. And again, you can check, is the queue empty or not? In a queue, you can't insert an element in the middle of the queue. There is no operation for this. Priority queue, arrange elements according to some priorities, some values. Each element has a priority. So you can, these container adapters have by default at the base the vector, I think. You can change the default if you want, but the vector is good enough. You don't have to worry what is behind. When you declare a stack, you have to specify the elements for the stack. In this case, we have integers, and you can declare whatever crosses your mind, stacks of integers and vector of integers. So each element is made of an int and a vector, and so on. Stack of whatever. It's possible to use them, not very easy to work with them. And I haven't seen applications really using these nested things. So we have seen that there are many containers. The question is which one to use when. Correct answer depends on the task. Nothing is easy, right? Whatever you have to do dictates what type of container you use. But I have put it together. Use a vector. For 2, 3, 4, if you have to use some containers, the vector is the one to use. And for lab, you will have some practice with a vector. There is a small question about using a vector in the final exam, so please pay attention to your lab question, because we don't practice with vector anywhere else except in the lab. But there is a small question to write some code using a vector, nothing else from STL. It's the most powerful. It provides random access. But if you remove or insert a lot at the front, the vector is not good. Insert and remove elements at the beginning and the end, you should use a double-ended queue. So if you work with the ends of the sequence, because this is where the double-ended queue is good. And it has the advantage that it shrinks when elements are removed, which doesn't happen for the vector. So, as I mentioned before, memory, if memory is an issue, you don't have enough memory, or you work with big containers, then memory can become an issue. And in that case, you might want to shrink the container to have enough memory to work. If you work a lot in the middle of the container, the least is to be used. This is the most efficient. If you do a lot of searching, trying to find elements, then a set or a map. The map is called in other languages dictionary. So a dictionary from Python is in fact a map in C++. Right, so we have looked at containers, a subset of containers. The most useful vector list double-ended queue, and then you should know what are the main differences between these sequence containers and these associative containers. Container vectors are there just to help you, maybe if you are taking data structure, to know that you have stacks, queues, and lists available. Stacks, queues, and priority queues available as containers in C++. And you can use them. You don't have to create them from scratch. So this is what we have for our discussion about containers. And we have a 3-minute fun moment. Okay. And the one fun, this might not work. Bad day. Oh, let's see if it's working. Installed, sorry, it was not the funny part. It was not, it requires some software to install next time. Speaking of assignment to solve, you might get very frustrated. Oops. Yep. Definitely not to do the lab. Definitely, but anyway. So we go for iterators, and settings. We will look at this notion, and you have to be aware there are two things which are called iterators. One is a hierarchy, and another one is a class, a set of classes. But we all call these iterators. I said that C1117 will make standard iterator obsolete. But this is a small part of iterators. It's a small part. Anyway, if you look at this iterator CPP reference, it's coming. You will see that the first explanation of the system is very slow. Yeah, it's a reference thing I put as a reference. Come on, go on. Today. You can see that the class iterator has here some predefined value, okay? As a template, it takes 2, 4, 5 arguments, 5 parameters, but 1, 2, 3 got default values. This is the type of the element, value type is called. And if you go and look at the definition, you will notice that it has all. All it has is just this, it's a structure. Notice it's the end of the class here. It's a structure, everything is public. And everything is made up of types here. It's not a proper class with methods and stuff like that. I call this a category. It tells us distance means what is the distance between two consecutive locations. And for integers, consecutive location has some size, for double, some other size. So this is, which is kind of used there. Pointer, it's what you know from C programming language reference from C++. Category is what we will talk about. Category is a classification specifying what operators the iterator should provide. What operators? Input operators provide only plus plus. Okay. So this is category, a specification of operators. And these are things which are used to define what was a simple iterator. But then we will see that vector comes with its own iterator class, where the pointer is defined in a specific way. Iterator category is bidirectional because the vector, it's random iterator because it has a lot of operators, plus, minus, plus n, pointer arithmetic, as you know it. So this, which I show you here, it's not implemented with a class structure, okay? And then you have this category of iterators: input iterator, output, forward, bidirectional, random access. So these are groups which refer to what operators we have. The weakest, the smallest number of operators provided are by input iterator. And as we go forward, the iterator will provide all operators provided by this and this. Bidirectional will provide all operators provided by this. Random access provides this plus something else. The same happens for bidirectional. You will see, provide everything with the forward iterator provide plus something else. But it's not inheritance. It's just conditions about operators. Okay, and this is a thing. And this allows algorithm to work on various containers, as long as the container provide an iterator which promise to come with operators as in these groups. We will see in a second what does this mean. So, common interface to access different containers. So iterators allow moving through a container without, in algorithm, without the algorithm knowing exactly that it's going to work with integers or with float or with string. This is the role of these iterators. They are similar to pointers when they come as classes. And here, I remind you how you work with pointers in C, and you can work with pointers in C++ as well. If we have an array of integers, normal C array, declare it, assign values, right? So we end up with the values 0 to 9 here. Now, instead of working with index operator, we can work with a walker pointer, a pointer to move through the elements of the array. And this is the best model for what an iterator does. So we start with a pointer at the beginning of the array, at the beginning address of array 0. This is the way to do it, or this syntax, they are equivalent, right? This is what happened in C, and you know this. And then we go with various tests, but the test which is relevant for our discussion is we look that the pointer has reached past the end of the array. Array plus 10 is past the last significant element of the array. The last significant element of the array is array 9, correct? Well, this is array 10. So we start at the beginning and we go with while loop till the last significant. When we reach the one after the last significant, we get out of the while loop, right? And what we do, we dereference our pointer to see what was stored there. And then we move to the next location, right? So we start at the beginning. This is not 1 past the end. We dereference it, so we will have 0 display and space, and then we move to the next element, which will be 1. So we are at location 1 in the array. We compare with location 10. They are not equal. Dereference, move to next location, location 2 is 10, and so on and so forth. This is how this model was used to design iterators. As you can see here, instead of working with C arrays, we work with a vector. Vector of integers, we construct our vector. Remember I said avoid index for vector construction, use pushback, okay? So we end up with exactly the same element as before. The upside is that we can extend the number of elements with no worries. We don't have to allocate memory ourselves. The system will allocate. If we want to work with more than 10 elements, we want to work with 100 or somewhere here, the vector will take it, not the arrays. C arrays are not so everywhere. To move through each element in the array, we use this tool, which is very efficient. Index operator can be used for vector. It's calling a function, as we have seen for index. But with our iterator, we are moving much faster because we are working with memory locations. So, to declare an iterator, notice iterator for the vector of integers. With this declaration, the iterator will know that we are working with int types. We know how to, the distance between integers, what is the distance, what is the value of the element. So at this moment we are working with a class. And this is a type, iterator for vector of int. This is a name we have chosen for our iterator. So this is a type, and this is the name of the variable. You choose the name, and you initialize it. And it's normal to initialize at the beginning of our vector. So the method begin comes from the vector itself and returns an iterator. Returns an iterator. That's why we can assign it. A shortcut. You put auto here. IT equals G begin. Auto means this gets whatever type is returned by this function. Auto is a shortcut. So there are two options. One is to use auto, or the other one is to use type def. If you want, so this would be equivalent to say auto IT equals V begin. And with this notation, IT will get this type. This happens with type inference. C++ 11 is able to do it. Another one would be to type def and call this long name something. Vector of int, iterator, and you give a name, my int, iterator. So you can use type def. These are the two methods which are used to shortcut code. Give a shorter name, and then from now on for vector iterator, you can use that name you gave, or you use auto. Anyway, so now we have our iterator set up at the beginning of our vector, and what we do, we move through the vector from the first one through each element plus IT means move to the next element. Okay, till we reach the end. If IT is equal to the end, this is skipped and we are getting out. As long as IT is not at the end, we display where IT points to, dereference your iterator, like for the pointers, and move to the next location. Okay. So this is typical way to use iterators. And you should somehow be able to work with both iterators and index operator. So you can move from this code to use index operator to perform these tasks, or from index operator used here, you should be able to move to use iterators for vectors. Right. If we want to move through a vector, we have to use the matching iterator, right? The matching iterator. So be aware, each container comes with its own iterators. Vector has iterators, strings has iterators. Strings have iterators. You can declare a string variable and use iterators for strings because it's a container. A string is a container of characters. List, every container has iterators. Right, so this was. Now, I said that we have on one hand classes, like vector iterator is a class of iterators associated to vectors. But we have concepts. What type of operations should iterator provide such that specific algorithms work? To, for example, output data. When you go through a vector or a group of elements to output data, all you have to do is be able to move forward, start at the beginning, move to the first element, displayed. Go to the next one, displayed. Go to the next one, displayed. So what operations do you need? Move forward and output, right? Write data. This is what output iterators provide. Forward iterators provide reading and writing. This does only writing. This does reading and writing. Bidirectional iterators move up, next, move behind. Bidirectional means it can move in both directions and can perform output and input. So for these iterators, we can perform all operations here, plus moving backward. Now, random access is, as I said, the most powerful. It can do everything which was done like this, plus jumping. I am here, I can move 5 places. And if I am here, I can move 10 places back. This is called random access, jumping all over the place. And what is the idea? Each feature adds new complexity. Okay, this is the most powerful, but it can be slow in some cases because you have a lot of functionality. If you need only just outputting, better use output iterators. It comes with a limited set of data of operators, and it's very efficient for those things. So input iterators, you can dereference with this notation. Each iterator has dereferencing. It comes equipped with this operation. And access member in the element. And you can move forward, pre-increment, post-increment. But this means move next. Each notation is equally efficient. As you can see, you can test for equality, non-equality. Or you can test that the iterators point to the same location or not. So this is the simplest concept. random access will have all this operation plus something. So what we put here in place are some conditions for various classes of iterators to implement. If an iterator provides only these operators, all we can do with it is to display to the screen, input iterator, to read data from the file or from the keyboard. Because we perform input and we read one element, then move next to read the next element, move next. We don't go back to read the previous element again. This is what input iterator. Output, write the value. It does the writing. So input and output somehow are equally weak. They provide this writing. You assign something to the location to which this points, and then you are allowed to move forward. Okay. Right. And as you can see, iStream iterator is used for reading data from the standard input. You have to initialize it. This is a type of our input iterator, iStream iterator, and it's meant to read double value. This is a name I gave it, and we associate it to the standard device. You can associate it to a file if you want. And then value 1 reads whatever was entered by the keyboard from the user, and value 1 is placed in memory, which is obtained from the user's entered value. And then we move to the next location, iterator, and the user enter another value, and that is stored there. So the user has to know that it has to enter 2 double values. With this, the first is read. You have to move to the next one to allow for reading the next value. If you want to display something, you have an OStream iterator, which is displaying double values. And as you can see, we put a separator here. We associate our output iterator to the standard output device, and we want to separate data by comma. You can put whatever symbol, whatever you want here. So with this, after the user has entered these values, now I can send value 1 to the stream, to the monitor with this OIT reference gets the value 1 and displays it. And I move to the next one, next location. So this is a typo. We move to the next location and display the next value which was entered. So this is a very simple explanation of how you can use iterators, and then we stop here. Forward iterators and talk about them on Monday. So please make sure that you finish your assignment on time. And if you have questions, you can ask by email like before. You can ask in the tutorial like before. But please do not leave it to the last moment. Do not leave it to the last moment.